Good morning, good afternoon, or good evening, everyone, wherever you might be. Today we're going to be now talking about equations of lines and planes. So last time we talked about vectors, the concept of vectors, the dot product, and the cross product. Okay, so yeah, let's just dive right into it. So equations of lines and planes. So first we're going to be talking about lines. So for this video, we're going to be talking about lines. For the next video, we're going to be talking about planes. Okay, so a line in the xy plane is determined when a point on the line and the direction of the line, its slope or angle of inclination, are given, right? So we're saying here that a line in some plane, so let's say in the xy plane, is determined when a point on the line and direction are given, and the direction of the line. Right? So direction meaning their slope. And so from there, the equation of the line can then be written using point slope form. So point slope form is this thing. Or no, actually it was the y equals some m, some x minus some given x plus some y. So this is point slope form, this one, right? Because we have 2 points here and we know the slope. The other one was point slope and slope intercept form. So this is when you're given maybe a y-intercept and the slope. So again, it depends on what information you have. Then you can make an equation of the line. Okay, likewise, a line in 3D. So I'm gonna say for here, can be written in point slope form. Okay, likewise. So likewise, a line L. So we're just giving it a name. A line L in 3D space. So how do we know if it's a line in 3D? So it's determined. So the previous one was a 2D. So what are the indicators that a line L is in 3D space? When we know that we have a point that's an ordered triple, so when a point, we'll just call it P. Let's say we have x naught, y naught, z naught. Let's call it P naught. So we have P naught, but P naught uh, on L and a direction of L. So pretty sure this is where the concept of vectors come into play, but we'll see. And a direction for L. So we not only need a point, but we need some sort of direction that the point is going to. Oh, and I'm right, yeah, which is conveniently described by a vector parallel to the line. So this is a vector parallel to the line. So all that's saying is we need a point and we need some sort of direction that's going to and that's a vector in this case. Okay, too many wordings. Okay. So here we let P XYZ be an arbitrary point on L. Okay, let's just write this out. So here we're sketching a scenario. So we're saying here that actually I'm gonna go ahead and take a screenshot of the picture that we're going to be referring to. So that we won't get confused. Or at least I won't get confused. I'm a visual guy. Okay. So here we say we let P XYZ. So we're referring to this point here. This is an arbitrary point. Arbitrary meaning it can be any point. So arbitrary point. And what do we know about this point? It's on L. This line L, right? The point is here. It's on L. And what's next? Okay, we let R naught. So I call it naught. The zero at the bottom. Basically, it's a subset zero. And R be the positive vectors. Okay, too much wording. Let R naught. So R naught is this thing right here. Oops. I drew it a different way. That's R naught. And R, so R is the blue vector. What are they? Well, they are positive vectors of P naught and P. P positive vectors of P naught and P. How are they positive vectors? Well, here we can see R naught is pointing towards the P naught point, and R is pointing to this P point. And I can, they're probably positive because they go up. I mean, if you look at this, there's no change in X, I think, but there's a positive change in Y and Z. And same goes for this one. There's a positive change in Y and Z. So that's interesting. Oh, I think we're trying to find the equation of line L. Yeah. Okay. So they have representations of the vector OP naught and OP. So I'm saying that R naught is a positive vector to P naught. That's basically a representation. So the representations for this is OP naught because it goes from here to here, right? O to P naught. O for origin to P naught. And that's a vector. Oh. And what's the other one? R, highlighting it differently. R to P. Love that. That's O to P. I'm gonna move. Voila, we have vectors. Okay, and what are we saying here? Let's say if A, so we see A here. I don't know why they highlighted it in black, but whatever. If A is vector, this also has a representation, right? What is it? Well, here we start at P naught and we go to its tip or its head to P. So P naught to P. P naught to P. P naught to P. Right? Because you go from P naught all the way to P. Same goes from the original. We go from O to P naught, O to P naught, and the other one was O to P. So A, vector A has this representation of P naught to P. Triangle law. Oh, well, that you have a triangle law. Then triangle law. Triangle, can't spell triangle. Triangle law for vector addition. This gives us, what does it give us? R equals R naught plus A. And this makes sense, right? Because we start from, so we remember that old example of mine. We start from here, we move here, we go here, which is basically equal to this thing. So we remember we start from Seattle, we go to Tacoma, we end up at Bothell. So I could either choose to go first to Tacoma, then to Bothell, or I could go directly to Bothell, right? Okay. So yeah, that's what the triangle law is. R is basically R naught plus A. So it's just describing what's happening in that figure that I showed you. Okay. Love this. Since A and V, I wonder where that came from. Oh no, never mind. Love this. This is A. This is V. What do we notice? They're parallel. So since A and V are, as I said, parallel, I was like, where did V come from? They are parallel vectors. There is some scalar. Yeah, I mean, there is a scalar that changes the length or magnitude of a vector. So let's just name it T. Don't know why they didn't name it C, but there's a scalar T such that A is equal to T times V. We're scaling V by T, which will give us A, right? And so from there, we actually have our first, I don't know what you call this, first like formula. R is R naught plus dV. Because remember the R equals R naught plus A, we just change A to dV. What is this equation for? Which is a vector equation. So we're getting there, the lines, which is a vector equation of L. And what are we saying here? Each value of the parameter T, so each value of T, based on T, it gives the position vector R of a point on L. What? Okay, I'm not gonna write that out. I'm going to keep reading and then I'll write what seems important. In other words, as T varies, line is traced out by uh, the tip of the vector R. As figure 2 indicates, positive values of T correspond to points on L that lie on one side of P naught, whereas negative lies on the other side of P naught. Okay, so what this is basically saying is based on our value for t, it gives the position vector r of a point on L. What do I mean by that? I'm just going to show the picture. So based on this picture, what it's trying to say, I think, is that if we plug in a t, this vector equation, we plug in any t, whether it's negative, 0, or positive, we get a corresponding r, right? But I don't see where's r here, so that's confusing. I mean, if we plug in 0 for t, then we get r equals r naught. And r equals r naught. So this is r. Because r equals r naught, right? Let's say we plug a 0 for t. So we get r equals r naught. So we get this thing there. That's why here it's t equals 0. If you plug in something greater, then we're going to get these guys here. If you plug in something less, then we're going to get something here. Right? And if we keep plugging in all of those stuff, we basically get this thing, which is oh shoot. We basically get this thing, which is a line. So that's how we're gonna get the equation of a line in 3D using a vector equation. That's my understanding of it, but you guys can correct me. Yeah, so that's that. Okay, so if the vector v that gives the direction of line L is written in component form. Oh, we can write this in component form. That's crazy. Okay, I'm just gonna write out this first thing. So each value of parameter t, I'm not gonna write parameter. Each value of t gives position vector r of a point on L. So we remember r is a position vector because its initial point or tail, I think it was tail, tail starts at the origin. So its position vector, it gives a position vector r of a particular point on line L. Okay. I'm gonna go down here. If the vector v, I think this is in our vector equation, that gives direction to line L is written in component form. So we're going to write vector v in component form, and it's what? ABC. Wow, very original. ABC. So those are its components. Then if we scale it by t, we basically multiply t to each component. tb, ta, tb, tc. Right? So, oh, we're just converting the vector equation into its component form. So that's tv. We can also write r as x, y, z. Could be any, honestly. And r naught as x naught, y naught, z naught. Right? So based on these I don't know, vector translations because we're translating it into the component. So vector equation, what is our vector equation now? Becomes, so R x, y, z equals R naught. So x naught, y naught, z naught plus dv, dA, dv. Oh, I'm doing it as subsets, but dA, dv, dc. Right? Now we can add it. So we're going to say, yeah, the textbook did it directly, but I'm just doing it step by step. X naught plus dA. So we're adding these two vectors, right? Y naught plus dB, Z naught plus DC. So there, we have our, we have the same vector equation, but in component form. And from there, two vectors are equal if and only if corresponding components are equal. I have yet to completely understand what that means. Or I'm just, my brain's not braining. Two vectors are equal. Oh, we're proving that this and this is equal, are equal. If corresponding components, yeah, that makes perfect sense. If their x component is equal, y and z are equal, right, that makes sense. So we have three scalar equations from here. We say that this x is equal to x naught plus dA, and so on and so forth, right? So therefore, we have three scalar equations. Scalar meaning gives us a number. So we have, let's write it here. We have x equals x naught plus dA. We have y equals y naught plus dB. And we have z equals z naught plus dc. Oh, he wrote it in reverse. He did AT, BT, CT, but that's fine. And here we say t is any real number. Okay. And these equations are called parametric equations. So we've heard of that from pre-calculus, from algebra. Okay. So these equations, these are called parametric equations. Of line L through point we have P, the initial point actually, P naught. Oh shoot, no space. Through point B naught, X naught, Y naught, Z naught. So they're passing through the initial point and they're also parallel to the V vector. To vector V. And vector V is based on what we've denoted it to, it has components A, B, C. And we're saying here each value of t gives a point x, y, z on L. Right? So we're saying each value of t. So based on our t, it gives us a point. Some point x, y, and z on L. So this is lines. All we're doing is lines in 3D. Okay, let's solve this. Yeah, I'm going through an example. Oh, we're gonna go through an example. Okay, so to summarize, so we're saying that parametric equations, we call them parametric is because we have parameters. So here are parameters t. Based on some t, we're gonna get some point in some line. So parametric equations for a line through point or through p naught. I'm just gonna be specific. Through point x, oh shoot, x naught, y naught, z naught. Wow, not working. Z naught uh, for a line through the point, through the initial point and parallel to, so we call it a, no, we call it a direction vector. At the end of the day, it's just a vector. I guess they're trying to emphasize. So what are the parametric equations for a line? What is this one? X equals x naught plus at, y equals y naught plus bt, c, what am I saying c? Z equals z naught plus ct. Okay, I'm gonna move this a bit. Taking too much space here. All right. And then, great. So that's that. Oh, that didn't grow. Okay. All right. Now we go to an example here. So example one. Uh, so we want to, for letter A, we want to find a vector equation uh, and parametric equations for the line that passes through point 5, 1, 3. Okay. So here we actually just use the formula that we got. So a vector equation is this right here. R equals R naught. I'm going to try this on my own first before looking at the answer. R equals R naught plus dv. And to be more specific, xyz is x naught plus ap, y naught plus dv. These are parametric equations of xyz. Okay. So this is our initial point. So first I'm gonna oh, I haven't finished the question. This why was so weird. So we're saying and is parallel So what is it parallel to? Vector, we'll just probably call it V or something. I plus 4j minus 2k. So here it's all about substituting the formulas. So first thing we're gonna do is find a vector equation. And then from there we can actually find the parametric equations. So we're gonna use that formula that we got, which is R naught plus dv, right? Then we have R is xyz, R naught is x naught, obviously, y naught, z naught. So this is our initial, right? It's our initial point-ish. Yeah, no. Oh yeah. And then our DATBTC plus is gonna write let's write AT, BT, CT. And then we can combine those guys. Okay. So here we say that 513 is our initial point. Or is it? Yeah, it's probably that. Yeah, passes through the initial point. R naught is a vector pointing to the initial point. It's actually a position vector. So here we're saying 513 is this. XYZ, I have no idea what that is. ATBTCT is this vector here, right? So you actually have our initial point, which has x naught, y naught, z naught, is actually just 513. So that means our R naught is this vector here, which is the vector 513, because that's the distance from the origin. That's the position vector. So we got R naught. Now we want to find ATBTCT. So here our V is actually this thing right here, because it's parallel to this vector. So 1 plus 4j minus 2k. In vector form, that's 1, 4, negative 2, right? And so if we want to add the dv, then that's just going to be t, 4t, negative 2t. And so our vector equation is going to be xyz, which is x naught, y naught, z naught. We're adding it to dv. So t, 4t, 2t, or negative 2t. And that's that. Okay, so you wrote it a different way using IJK form, which is totally fine, right? I'm gonna write it. Let's try writing it his way, or at least the textbook way. So what they did was they converted R naught in IJK. Oh, okay. They converted it to IJK, and then they just switched the values around, and then they got parametric equations out of it. Actually, you know what? It's fine. I'm just gonna get the parametric equations. Okay, so parametric um, equations. So Okay, that's our vector equation. So we want to find parametric equations. So actually, from our formula here, we can just add them together. This x naught plus at equals x. So that's what I'm going to do. X is 5 plus t. Y is 1 plus 4t. Z is 3 minus 2t. Yeah, and then that's the same thing we got. Or the textbook got. So that's the answer. So we get x is equal to 5 plus t. Y is equal to 1 plus 4t. And then same goes for z. Z equals 3 minus, because it's plus negative 2t. And plus negative 2t is just minus 2t. So that's that. Okay. So boom, we have that. Now the next thing we want to do is we want to find two other points on the line. So honestly, here we just plug in a t, and then we get something out of it. Okay. Yeah, so we just choose a value of t. So we're going to say if t is equal to 1, then our x is 5 plus 1, which is 6. Y is 1 plus 4, which is 5. Z is 3 minus 2, which is 1. And so this gives us a point. So 6, 5, 1. So that's a point on the line. Another value we can plug in is if t is negative 1. What's that going to look like? Well, that's x equals 5 minus 1. So that's 4. Y is 1 minus 4. So that's negative 3. And z is 3 minus, or 3 plus 2. That's minus 2 times negative 1 is plus 2. So 3 plus 2, which is 5. And so another point could be 4, negative 3, 5. Rather than vector, that's funny. So we have that other point. So we're using these parametric equations to get x, y, and z coordinates. Right. Okay. The vector equation and parametric equations of a line are not unique. So if we change the point or the parameter, or choose a different parallel vector, then the equations change. So for instance, if instead of 513, we choose the point 651. Don't know where that came from. 513. Oh, so if we change our initial point, if we change it to, let's say, the 651, then our parametric equations will become different, obviously, right? Here, look at this. If we change it to 651, this 5, 1, and 3 is going to be instead 6, 5, and 1. So those are different parametric equations, and they definitely give different values. So that's the thing. If you change the parametric equations and the vector equations, then everything's going to change basically. Or even if we choose to stay with 513, the 513 there, but we have a different parallel vector, right? Let's say we change this thing right here into It says here 2i plus 8 minus 4. I don't even want to write that out. Um, oh, here, they wrote it 1 plus 4 minus 2. So here it's 2 plus 8 minus 4. Then our parametric equations will also be different in terms of the parallel vector. And so that's also going to give us different values. So the idea is, okay. In general, if a vector v is used to describe the direction of a line L, then A, B, and C are called direction numbers. Oh, we're getting into general stuff here. So let's just go through that. So we're going to say, in general, let's say we're given a vector B with components A, B, C, and it is used to describe direction. Oh, I was writing correctly. So it's used to describe the direction of some line L, then A, B, and C, so we call them numbers. They're actually called direction numbers. Probably gonna highlight that maybe. Yeah, let's highlight it in red. Okay, so they're direction numbers of L. Why am I just highlighted it in red and I changed that back to this here. Okay, since any vector parallel to V could also be used, because we have different parallels, right? We see that any three numbers proportional to ABC could also be used as a set of direction numbers for L. So if we even scale the vector, so let's say we have like what? 2, 4, 6. So that could also be 1, 2, 3, because they're proportional to each other. They could also be used as a set of direction numbers for L. So it's probably going to be the same thing, hopefully. But yeah. Okay, so another way of describing a line L is to eliminate the parameter t from equations 2. And if none of them, A, B, and C, if none of A, B, or C is 0, we can solve each for equations of t. Okay. Oh, this is another idea. Okay. I also bamboozled with the. So yeah. If we have a different parallel vector, but it's proportional, then they could also be used as a set of direction numbers for L. Okay. And another way of describing line L is to eliminate parameter t. So here, we're not just, we can also try to get the time itself. I call it t time. Try to get t itself instead of, because for instance, like you're given coordinates, you're given x, y, z coordinates. You want to find t sometimes. So you're not always given a t. So this is just another way of looking at it. And we're saying here, if none of A, B, or C is 0, we can solve for t. And ideally, if they have the same coordinates, then they should have the same t. So how do we do that? Well, let's look at one. X is, what was X again? I totally forgot. X naught, the initial point maybe? Yeah, X naught plus some multiplier of t, AT. So we want to isolate t. So this is going to be X minus X naught all over A, which is t. And same idea for the others. So I'm just gonna write all of it out. So t is actually this thing. T could also be in terms of y. I think that was b. Or in terms of z. And here, well, from here, we actually obtain something nice here, which is that since they are all equal to t, then that must mean they are all equal to each other. Right? And these equations are called symmetric equations because they're equal. And we notice that A, B, and C are denominators and they are direction numbers of L. And they are components of a vector parallel to L. And so if one of them is 0, we can actually still eliminate T, right? So I'm going to write all of what I just said. So these are called symmetric equations of L. And we notice that the numbers A, B, and C A, B, and C are direction numbers of L. Right? And so that means there are components of a vector parallel to L. So let's say if one of A, B, and C, A, B, or C is 0, we can still eliminate T. We can still eliminate T. Okay, so let's try an example here. So let's say if A is 0, then equations of L are as follows. So since A is 0, we can't really write x equals x minus x naught divided by 0 because that's going to be undefined. So what we're going to do is x is x naught. That's it. X is going to stay the initial point. And why not? That's divided by b is equal to z. And what does that entail? So this means L lies in the vertical plane. So a plane that's vertical, and that plane is x is x naught. Okay, let's move on to example 2. So example 2, we want to find parametric equations. And symmetric equations. of the line that passes through so it passes through points A, 2, 4, -3, and B. B in this case is 3, -1, 1. Okay. So how do we do this? Well, we can probably just use the formulas, right? I think we can use the formulas. Um, so we're given 2 points, A and B. We don't know what's the initial point. Um, okay. Let's see. Let's see. So we are not explicitly given a vector parallel to the line, but we observe that the vector v with representation AB is parallel to the line. So the idea here is we're trying to make a line that has points A and B, and it's a 3D line. And so we're probably going to represent that with a vector. So we're going to say we want to find this vector here that goes from A to B. And so again, how do we do that? We track the changes. So 3 minus 2 is 1, -1 minus 4 is -5, 1 minus -3, 1 plus 3 is 4. So those are the changes that you need to go from point A to point B. And so we have this vector here that's AB, right? Now we have a vector. Let's call this V. Let's call this V. Now we have that vector, and that's parallel to the line. And from here, we actually have direction numbers already. We have A is 1, B is -5, and C is +4. And we can take the point A, so 2, 4, -3, as B naught. And from there, we can see parametric equations and symmetric equations, right? Okay, so I'm going to list down the steps so that it's not confusing. The idea here is to first find a vector parallel, right? Because that's what we need. We need a vector that's parallel to the line, or to some line L, right? Okay, so now we have this thing. So we're going to say A is 1, B is -5, um, and C is 4. Okay, now what's next? We want to find initial point, P naught. And so P naught, which has these initial points, we can just use A, to be honest. We can just use that. And then now we can find parametric equations from here. We already have a vector. We just plug in a t there, and then we have p naught, right? So you have x is x naught, so 2. We're adding it to this component t. So t times 1 is just t. Y. initial y, so that's 4. We add it to negative 5t. So I'm probably going to say minus 5t. Yeah. And then for z, initial point is 4. I'm wrong. It's negative 3. I got it from here. And then 40. 40. Where did I get 4? Here. That's our vector parallel. And we just multiply t to make it into a parametric equation. So done. That's one of the steps. Next thing we want to do from here is we want to find symmetric equations, which we were able to derive a while ago. But we're going to say, I mean, you can just derive it from here. T is what? X minus 2 divided by 1. Do we need that? But yeah. And then what's this? Y is, I don't know, I should put this in terms of t. So I have y minus 4 over negative 5. Here, when we isolate t, what's this gonna look like? 5t is y plus 4. 5t is, oh no, it's just minus. It's minus 4. And so this just switches, 4 minus y. Then divide that by 5. So t is 4 minus y over 5. Then we can probably switch the signs again. So t is y minus 4, negative 5. So they're the same thing. 4 minus y over 5, y minus 4 over negative 5, same thing. I'm just checking because my textbook built differently. And z is z plus 3 over 4. Over 4. Right? Okay, I just realized. I think I've lost my screen. Anyway. So yeah, we have our symmetric equations. And yeah. Okay, now an interesting question that we have here. At what point does it intersect? At what point does this line intersect the xy plane? How do we know if it intersects the xy plane? Well, again, here we're talking about conditions. And so it intersects when z is equal to 0. So we're saying it intersects when z is equal to 0. And so we make z equal 0 in here, in our parametric equations. Right? So we're saying if z is 0, we have 0 plus 3 over 4. And so we have 3/4 for our t. And then we can plug in 3/4 in our parametric equations to get an x and a y coordinate. Right? So that's our t. So it intersects when t is 0. We have z plus 3 over 4. We change that to 0 plus 3 over 4. And so that's our t. And now from here, we want to find x, y. So x, y coordinates. So for x, we'll just use the parametric equation, t plus t. 2 plus 3 over 4. We get 11 over 4. For y, we get 4 minus 5t. So what is this? 4 minus 5t. Now we just plug in the 3/4. We get 15 4. We get 4, 16, 15, 4. We get 11. So there. I probably messed up somewhere. Oh, this is 1. 16 minus 5 is 1. 1/4. So it intersects. So I'm going to say line intersects xy plane at point, I call it S, point S, at point x value or y value or z value. 11/4, 11 over 4, 1 over 4, and 0. Or you can just put z in symmetric equations, and we get some value here, and then yeah. I mean, any of them work. I could use parametric equations, I could use symmetric equations, right? Okay. Okay. Let's do this part. So if you want to talk more generally, so in general, the procedure, for example, 2 shows that direction number of line L through points, the initial point and some other point. Yes, funny enough, it's just their differences. It's just their differences in points, right? Because if we notice here, we just looked at the difference of each of these points, 3 minus 1, -1 minus 4, 1 minus -3. And we get such vector, and those were our direction numbers, right? 3 minus 2 is 1. -1 minus 4 is -5. 1 minus -3 is +4. And so actually, these direction numbers, we can denote them as a difference of 2 points instead of just a vector that's parallel to some line, right? So here, what I'm saying is direction numbers, so A, B, C, right? So direction numbers of line L through, let's say, the initial point, right? And some other point. So let's say P naught. So that's a point. And let's say another point, just call it P1 for simplicity purposes. I know math is not creative. And they're basically the difference of those 2 points. X1 minus X naught, Y1 minus Y naught, Z1 minus Z naught. And these are what? A, B, C. A is X1 minus X naught, B is, you get the idea. And so we can actually generalize our symmetric equations. Symmetric equations of L are actually just these points. X minus X naught divided by, instead of A, we can just say X1 minus X naught. This is equal to these guys here, right? That's what we've noticed. So often we need a description not of an entire line, but of just a line segment. So, excuse me. How, for instance, could we describe the line segment AB in example 2? If we put t equals 0 in the parametric equations, then we get a corresponding point to 4 and -3. And if we put t equals 1, we get some other point. And so okay, this is just talking about an example here. So it's the idea of plugging in some t, we get 2 points, and then we can make parametric equations out of it. And then from those parametric equations, we can make a vector equation out of it. Okay, I'm not gonna go through that example anymore. I'm gonna go directly to the general part. So we're gonna talk about something more general about parametric and vector equations. So in general, we know, what do we know? We know that the vector equation of some line, oops, uh-oh, oh, wait, I think, uh-oh, my bad. My OneNote shut down for some reason. That's funny. This, I have no idea why my OneNote shut down. Okay, I can't share it? Can I share it? Sorry for the technical issues. Can I share it? Can I share it? Am I still recording? I'm still recording. Okay, I thought I lost. I lost recording or brown out again or something. Okay, so we know the vector equation of some line. Maybe I'm using OneNote too much. through uh through the vector R naught R naught in the direction of a vector V is R equals R naught plus TV or A or whatever, but it's TV. Right? We looked at it from this example here that the vector equation of a line. I'm gonna copy paste this because I'm trying to word it out in a way that makes sense to me. Uh-oh, don't know why I did that. I'm gonna copy paste this thing just so that I can see uh, what I'm exactly explaining here. So I'm gonna copy paste this. So we know that the vector equation of a line through vector R naught. So R naught is here. The vector equation of a line is this thing here, right here. This line L. In the direction of vector V. Vector V is this thing. Don't know why they didn't show it. But it was from a previous visual somewhere. Vector V is somewhere there. Let me check if I can find it. Oh, there you were. There. That's vector V. So it's something parallel. Um, but yeah. And we noted this equation from all of that stuff. I'm gonna take out the visual. It didn't show it in the text box. So, okay. So here's the new thing. If the line I don't know for what reason, but also passes through the tip of R1, we can actually take V equals R1 minus R naught. Right? So is there a visual of how that looks like? Because I have no idea what R1 looks like. Okay. Still trying to get in my head. I think this is the better visual. We have an R naught vector that's pointing towards this L. It's passing through. It gives us this corresponding point P naught. We have an R vector, and this is also passing through this point. I mean, this line L, it has X, Y, Z points or coordinates. And then we have a vector V that's parallel to L. And then from there, we were able to get vector representations. We did a triangle law here. And since A and V are parallel vectors, we can just scale A to be T times some V. And so we get this equation right here. And then from there, we know the vector equation of a line through the vector R naught in the direction of vector V is that equation that we just previously got. And if the line also passes through some R1, the tip of R1, then we can take V being R1 minus R naught. Maybe we can say, oh, I think I know what it means. Maybe. I might be wrong. But let's say this was R1. So this is S1, Y1, Z1, that's P1. If we subtract these two vectors here, what will it give us? The V, right? So actually, it doesn't feel all that wrong to do that. We're just making it more general as we can. So we can actually just subtract those two vectors, and that's actually just equal to V. And from there, we can translate vector equation into something else. And so vector equation is R is equal to R naught plus, we add it to T, R1 minus R naught. And then from here, we can simplify some stuff. So we actually get 1 minus T R naught plus R1. PR1. Oops. And this line segment is given by the parameter interval of T in between 0 and 1. Okay, so yeah. And then we have our last example, and then let's call it a day. I'll probably do something with planes later or tomorrow, but for now, we're really just talking about lines here. So yeah. Okay, so in general, so the summary of what I just talked about, and I'm still trying to absorb it, is that the line segment from R0 to R1. I think a visual would help, honestly. I don't have a visual here. So we have this line segment, and it's given by a vector. Probably understand it when we do an example after this. Uh, so we have R as a function of t here. Been a while since I've done functions again. R of t is what? 1 minus t. R not, I believe, plus t R1. And we have a condition that t is in between 0 and 1 inclusive. So that's the thing. Visually, I'm a visual person, so probably need more exercises or visuals to go with this. When I go through some exercises, I'll probably get this. Hopefully. Okay, let's solve this real quick. So here we have, so on an example, we have example 3. And here we want to show that lines L1 and L2 with parametric equations. Sometimes the textbook gives harder examples, which is funny. Okay, so we have L1, which has an equation of, has a parametric equation actually. 1 plus t. My y is -2 plus 3t. And my z is 4 minus t. Let's look at L2. What's my L2? X is 2s. What's my y? 3 plus s. What's my z? -3 plus 4s. Again, these are all parametric equations. If you look at this, wow. So I want to show, well, we want to show that both of these lines are what we call skew lines. Never heard of this before. And this basically, oh, at least they give it a definition. They do not intersect. So both lines do not intersect. And they're not parallel. So how can we prove that? Oh, another thing, if they don't intersect and they're not parallel, they also don't lie on the same plane. Interesting stuff here. Okay. So how do we do this? How do we prove that they're not parallel? We can actually look at their direction vectors here. So that's one thing we can do to prove they're not parallel. So first thing we can say about this is actually look at their changes in x, y, and z. Look at their vectors. So I'm going to say look at direction numbers or direction vectors. That's how we can say they're not parallel. So here we see that for L1, I'm going to write it in English. For L1, we have a direction vector. And if we look here, this is what the direction vector is. 1, I believe this is positive 3. Yeah. And then -1. So it actually has 1, 3, -1. Right? And for L2, we can also look at its direction vector. It's kind of a way of finding slope, but we can't really find slopes in 3D. That's why we use vectors. So what is this? 2s? 2s. So here it uses s instead of t. So here we have 2, 1, 4. So I'm looking at the numerical. I'm not gonna say some words. I don't even know what I'm saying. It's the number after the letter. A number before the letter. But yeah, so it's 2, 1, 4. And here we can see they are nowhere near parallel because they're not scalar multiples of each other. Right? It's not like you're given 1/2. This is actually the same as 2/4 because I can just scale the thing. I multiply 2 to both xy components and I get the same vector. Here I can't multiply anything with the same scalar, so we call it a scalar, to get the same direction vector. So they're not equal. So they are not parallel. So that's how we managed to prove that part. Actually, I'm gonna just say like not parallel. Okay. How do we prove they don't lie on the same plane? Well, okay. Well, we actually got this from a previous example, right? How do we know if they lie? Actually, we can check this. Oh no, we're only checking if it's parallel and if it intersects. If they're not both, then they don't lie on the same plane. That's the idea. So we're also going to check if they intersect. So here we check direction vectors to check if they're, my head's in the way, check if they're parallel. Right, put my head back. Okay, so they're not parallel. Next, we look at their intersection. So how do we do that? Well, we basically equate their parametric equations on their parametric equations. Why? To see if they intersect. So here we're checking if they intersect um, based on their parametric equations. Let's move this. Okay. This probably has enough space. All right. Why is it not moving? There we go. To see. Oh, to see if they're if they intersect. Okay, so for the x, we're going to equate those. For the y, we're going to equate those. For the z, we're going to equate those. Right? So how does this work? We have 1 plus t, because that's their x values, right? Is equal to 2s. We're going to find if at some point they intersect. But ideally, all of their x and y's should intersect. Negative 2t plus 3t equals 3 plus s. And then we have 4 minus t, which is negative 3 plus 4s. And the way we can check, well, we can actually solve for two of them. We get some t and we get some s here. So let's try to do that actually. So I guess s is just 1 plus t over 2. I just divide 2. And then from here we can say negative 2t plus 3. Really? It's 3t. Oh, it's minus 2 plus 3t. And plus 3t. This is minus 2 plus 3t. And this is actually equal to 3 plus s. And s is what? 1 over t, 1 plus t over 2. And now this is an equation that we can solve. So we just put all the t's in one side and all the other ones in the other side. So I'm going to solve for this thing here. So let's see. So this is 3t minus 1 plus t over 2. This is 3 plus 2, that's 5. Um, we can multiply by 2 so that we get rid of the fraction. So we get 6t minus 1 plus t here. This is 10 because I multiplied by 2. And then we have 6t minus 1 minus t is 10. We have 6t minus t, which is 5t. 5t. We have 10 plus 1, so we have 11. So t is just 11 over 5. So we got that solution there. Oops, I unmuted my mic for some reason. We got t is that value there. We're going to put in purple. And from there, we can actually plug into s. So s is 1 plus 11 over 2 divided by 2. We get some value here. So this is 20, no, 2 plus 2, 13 over 2, 13. Uh, I said 2, right? Oh my God, I meant 5. This is 5. So we got 5 over 5, 16 over 5, 16 over 5 over 2, 10, 16 over 10, divided by 2, 8, divided by 2, 5. So that's 8 over 5. So now we have some s and we have some t value. So if we try plugging it in this next one, it should satisfy, right? Yeah, so we got the s value here. And then if we plug it in, oh, this is unorganized. If we, how do I make it more organized? Maybe I'll put it here. This is solving for t basically. Probably put here. Yeah. So that's solving for t. I'm gonna say solving t. Solving t. This is solving s. Solving s. And then here I'm going to check if t and s values satisfy third equation. So what I'm saying is if I plug in the t and the s that I got from the previous two into here, then I should get the same thing, right? Because it's equal. So we're saying 4 minus 11/5, is it equal to negative 3 plus 4 times what? My s, 8/5. So what are we saying? I mean, what are we doing? Okay, let's just solve it. So it's 20 minus 19, 5. I'm still gonna put that question mark because I'm not sure. This is 32, I believe. This is 5, 15, 32. This is what? I my calculator. 17/5. Oh, what did you look at that? So we're saying that oh, what's happening? We're saying 19, the output of this one is not the same as the output of S. So they're not equal, so they don't intersect. So it's X, no intersection. So if they don't intersect and they're not parallel, then they lie on different planes, meaning they're skew lines. Okay, so that's that for now. Next video, I'm going to be talking about planes. I might actually go through some exercises of lines first, and then we move on to planes. But yeah, thank you guys for watching. I hope you guys learned something. I did. I'm a bit excited because we're finally getting to learn not just the basic vectors, cross products, dot products, but we're actually going into lines and planes, and we're trying to make sense of that with equations. So yeah, I'm looking forward to planes actually. Um, and hopefully it applies to something data science, but I'm still looking for that. But if you guys have any ideas of what I might read or really anything for me to learn, I'm happy to learn more about it. So yeah, that's it for today, and I'll see you guys in the next one.